um, or not in the lab, but try this separately. So Maddie will be joining today for session 6. Let me ping her. We have a first timers, so we always welcome everybody, but this is literally our last session. It's a very intense course, so sorry we cannot support anyone.
No worries.
Please look
I'm just
into other
concerned.
GDGs who are running a cloud. Roya, would you like to share about the new cloud architect that just started yesterday? You can join that one. But no, I cannot onboard you. I'm sorry, Ahmed.
No worries. Do you have any links for that? What you just mentioned?
So we are doing professional ML engineer, but I know Linda, is Linda still here? Linda and
Yeah,
Roya
I'm sharing now in the chat the romance
part of a
sessions.
cloud architect, which is honestly, that one is kind of foundational for anything you want to do professionally. So data engineer, ML engineer are more focused. If you are cloud architect, that's kind of the basis for anything. So they just started, so you can definitely
I pasted the link in chat for everyone who would
yeah.
like to join.
Hola, I love the Spanish greetings. I say hola a lot, even though I'm not Spanish. Uh, what else? So yeah, thank you for those who were ahead and testing, or not just testing, but doing the labs from session 1. Oh, good. Yeah. So I don't know of any ML engineer starting that one. I'm really thankful to Roy and Maddie who are doing this, because it's really advanced course. It's not something you can just learn overnight and start teaching. So I honestly don't know of other ML engineer courses running at the moment. But
Also, Anna, I
cloud,
posted in the chat the link of the playlist of all our sessions if anyone wants to go over the videos that we have from these ML sessions. It's in the
that's
chat.
cool. Oh, I see we are recording already. I think these logistics are not really to be recorded, but whatever. Um, I was saying it was great to have Roya and Maddie as instructors, because um, being an ML engineer is amazing, but it's not something that can happen overnight, and you need both ML and cloud skills. So, whatever your plans are, though, the cloud architect is fantastic certificate to have. It's the top one in the entire industry, not just Google. So, and I got a lot of questions about your credits expiring. So if your credits for quick labs are expiring and you still want to do the labs, if you join another cloud certification program, like the one that Linda just posted, then your credits should continue, or if they have expired, you should get another 3 months. So that's definitely a way to continue your journey. Linda rocks. Yes, Linda is very special, very helpful. Without her, it would be very difficult to run this. So, anyone Let me open the Q&A so you can add your questions there. See if Maddie is around. One moment. Any other questions that you have around the labs? I post the tracker all the time. I know it loads, it's slow to load. So I know people have tried to load it. It does take a while. It definitely can be optimized. It does take a while. But I encourage you to use it to know what you still need to complete, and you can access all the required labs right from there. So Raya doesn't have voice. So let me post that link again. One second.
Yeah, I think they have to finish the labs by the 24th, right? August 24th one, right?
Yeah, so the I posted the tracker. So the tracker is for what you need to accomplish, the labs. It doesn't hours which we have between each session. So we do have office hours next week. We'll post the event shortly. So we will have a GDE, Google Developer Expert, Rabimba. He's been there before, so he can. I think he'll have presentation on NLP, Vertex AI, and you can also ask any last minute questions. Hello from Atlanta. Finish everything. Whoa, Shafan, if you finish by the 20th, that would be fantastic. But you do have until 24th. So, what else? Yes, so I will wait until 24th to get the final count, which I'm supposed to send to the Google team, and then we'll get a voucher. It's a code basically for everyone who completes all the labs. Uh, Again, I don't think the ML. Oh, Samira completed everything. So the ML pipelines have been a challenge. I think Volkan posted that he has. Does somebody have a workaround? I know there was a big discussion for TensorFlow extended being the lab is giving errors and it's outdated. So the ML pipelines, we are not gonna. I already commented. We are gonna exclude them, but ML ops is pretty essential. So if you wanna pass the exam, you'll be uh, better off, doing those topics and having experience in that. So if somebody has a workaround or solution, please share. No? The US Central. Um, 1 second, I have to take a call. Can Linda or Roya look into this? I know US Central one is usually overloaded because everybody uses it.
I think somebody already answered in the chat. Still.
But sometimes you don't get the credit if you change. Sometimes you have to use what they suggest. So
Yeah, I guess for the validation, so you can pass the.
yeah, you can use
Right.
any region as long as it passes the validation.
Yeah, I see that Yash Jane answered what. So he switched from, or she, I don't know, switched from one from US West one to US East one, and it worked for.
Yeah, if you can switch the location and that valid to use whatever they're suggesting. I see Rich says he uses even European ones. Oh, good. Okay. Oh, Maddie's here. That's awesome.
Yep, I've been kind of waiting for people to like discuss their struggles, because that's one of the key reasons we do this for peer support. Um, so we can all be emotional support animals for each other. But yeah, do we want to go over the content for this week real quick, and then Roya has very graciously decided to join us for the last session. So I figure we can go over the existing content, go over a couple questions that they have provided for us, and briefly maybe review some of the key points that I think like is worth looking into and probably will be on the test. And then we can open up for Q&A, and then me, Anna, and Roya will all be here to answer your questions. How does that sound for people? Thumbs up, thumbs down. B for thumbs up. P for not good, thumbs down. Okay, there's a vote. Legit. Okay. If you have specific topics you would want us to cover that you think is more valuable, then definitely throw it in the chat as well. Cool. I'm not seeing a ton of suggested topics, so I guess we'll go with that. If folks have questions, obviously feel free to chime in. Okay, so I will figure out how to share my screen. Okay, ML pipelines. Yes, I hear you. And okay, share my screen. And my apologies, this computer struggles really hard every time I try to use screen sharing. So hopefully everyone's able to see my screen now. Okay, so I guess enough. So we start with a quick review of where screen's frozen again. My apologies. So you're very familiar with this chart by now. Some of these labs are, unfortunately had to get changed. One thing I do want to point out is that sometimes the labs are not required because they don't work or API changes that causes the labs to be like out of commission. Just because they're not a part of this official learning pass, and just because we're not checking your completion because you can complete it for the voucher, doesn't mean it's not a good idea to review those labs, right? So, for example, I know people struggled a lot with getting what they call pipelines to work with what they call the AI platform. But it seems to me like Google has decided to really like offer a managed service, and that's what they're starting to call Vertex AI, right? So the way I would approach it is that look at the labs that they're asking you to do, and then look at the key points, right? See if you can figure out how to do that, or find an equivalent lab that works on Vertex AI. Because when you review the exam guide and when you look at the key topics, it's the spirit of the law and not the wording of the law, right? Um, if a pipeline doesn't work for AI platform, then does it work for Vertex AI? If you can do something similar, then you're probably good to go. Another thing I want to kind of like mention here for you to keeping in the back of your mind as you start to like prepare and study for that like final push for the exam is to understand the higher level frameworks, right? So in terms of machine learning, what are the key segments in the process? And then once you understand the higher level framework, then you can drill down to each section, and that will help to guide you for how you answer questions. A lot of the questions, based on my sampling of many versions of like sample tests online, a huge part of it is about what Google product you should use for that specific case. So you're always thinking about the trade-offs between the cost, how long it takes you to do the work, how annoying is it for you, what or a nice way of saying it is like maintenance burden for the engineers, how accurate is the final version, and how scalable is it. So for each of the kind of like steps, or for each of the segments in the pipeline, it's good to have a mental map of like, okay, these are products that Google offers. I would do something similar, but between these two, I would choose this one if I need more inference speed, and I would choose this one if I want lower cost, right? So being able to make those decisions really helps you, other than the actual like machine learning statistics basic stuff. So that would be my key takeaways. And for now, we're going to bounce around a little bit and talk about recommendation engine. I think in the last session, we were able to briefly describe what a recommendation engine does. And because this is one of the earliest, most well applied fields of artificial intelligence or machine learning, there's a ton of libraries for this. But I guess here it helps to understand the basics, right? So roughly there are three main kinds of recommendation engines. So one is content based. This is like when you go on Amazon, it says other users who viewed this also viewed something else or also bought something else, right? Clustering, and content based is sometimes what we like consider the traditional or the most like old school technique. Clustering is when you kind of like group based on similarity. And we briefly talked about in the last session when we're talking about both recommendations and natural language processing, how the embedding or the encoding process is very important to this, just to redo a capture, redo a summarization of that whole conversation. Machine learning is about how to represent the real world in a numerical representation so you can feed it into the model. And then what the model is actually doing is that it's building one way you can think about what the model's doing is building a kind of a numerical representation of the real world based on the numerical representation of the data, right? So not only is it looking at the data, it's starting to kind of form a function. It's starting to like map a function between what you're trying to put in as input and what you're trying to predict, right? So what it actually does is that it converts the input data into a lower dimensional representation, and sometimes we can call those embeddings. And based on the embeddings, which sometimes is a vector, or actually most of the time is a vector, you can compute similarities, right? So for example, if you were to compare a similarity of New York versus Syracuse, it should be closer in distance if this model has learned well to something like New York and I don't know, Alberta, something like that. One, because one's a city and the other is a province, and two, geographically they're not very close, right? So one way we frequently evaluate how good embedding is, because the embedding process is so critical for so many downstream tasks, is we actually just use the embedding that the model has learned, which is similar to an internal representation of the world, a simpler representation of the world to this neural network. And then we basically take embeddings and use that as input to do some downstream tasks, right? So if it's learned to classify cats and dogs, we should be able to use the image embedding to say, hey, this is a husky is closer to a German Shepherd, and it's not close to a ferret, because they're not even the same class of animals, and also ferrets are less commonly pets. So collaborative. So this is kind of like bouncing between the user and also the items, right? So usually when you have a recommendation kind of problem setup, there's usually like a two-sided market or a marketplace. You're trying to match the supply side and the demand side. So in Amazon, the supply is obviously stuff that you can buy, and then the demand is each individual users, right? So this is essentially you're learning the representation first for the items, and then you're freezing that and using that to learn a better representation for the items, and vice versa. So this is kind of the three different versions. Obviously, there are many like hybrid types. For example, there are recommenders that considers fairness and also newness to improve discovery, versus recommenders that just optimizes for one metric. And we briefly talked about how improving metrics and improving actually privacy protection for consumer data is a way to get better performing and more socially positive recommenders. So here are some examples. So items recommended for you. This is actually optimizing for click-through rate, right? So how do you define click-through rate numerically? It's roughly out of the entire list of things I showed you that you can click on, whether there are items you could buy, add to cart, whether there are news articles you can read, whether this is Google search results, how many of those did you actually click on? So that's one way we can define that. Now, there is a slightly different recommender problem that's called learning to rank, as in the order of which you're presented with these options also matters, right? As we know, as a dev, you very infrequently go past the third page of like Stack Overflow, because then something's probably like your search terms are probably not correct, right? So learning to rank is a slightly different version of recommender engines. You can think of it that way. So recommended for you, again, conversion rates, right? So once again, out of if it's a purchasing process that has multi steps, what is the conversion rate from one stage to another? So for those of us who unfortunately had to take marketing, I remember there's a marketing model called AIDA. It's attention, interest, and then the rest I don't know. I didn't pay attention. So you're measuring conversion from how many people landed on our site did we grab their attention, and out of the people that we have their attention, how many people do we get to become interested, right? And eventually, obviously, the last one is someone purchased into someone converted from just a general member of the public into an actual buyer, right? So once again, other items you may like, click-through rates, other items you may like, conversion rates, frequently bought together, this is revenue per order. So this is a little bit more interesting because you're now kind of constructing a set, right? So one example of this would be you can buy a vacuum independently and then a filter, but you can also buy the vacuum that comes all in one with a filter, right? So sometimes maybe like if you did all the research and did a spreadsheet, it's actually better for you if you just buy the more expensive one with the filter. But if you're Amazon, you may be like, well, less people ended up buying, don't want to spend a lot of money up front. So it's actually better to recommend a vacuum with a replaceable filter instead. So that's just a random example I made up for how revenue per order would make sense, right? One thing that you will notice is that the recommendation engine like field has basically only 2 or 3 metrics to optimize. And this is actually one of the reasons why recommendation engines have, got a lot of bad press for what they're doing to society, right? It's because if this is the only information they can measure as a proxy of like how well they're doing as a product to you, the user, that's what they're going to use, right? So this is why sometimes results are not perfect. Another kind of random topic that we're going to talk about in week 6 is hyperparameter tuning. This is very closely tied to another topic that a lot of people are interested in, which is called AutoML, right? Automated machine learning. So let's talk a little bit about what exactly are considered hyperparameters. Hyperparameters, to me, are essentially values that are outside of the model that do not get updated through the training rounds, right? So thinking back to your regression example, you are trying to plot a line best fit with y equals ax plus b or mx plus b, depending on where like what notations you use in your books. You can have 2 parameters in m, which is the slope, and then the b, which is the intercept, right? So those are actually parameters of the model, and they will get updated as you do model training. But something like learning rate is something you typically set up front, and is not an optimization that is actually for the model to learn. There are ways of doing like optimized learning rates, kind of like selection, but then that requires you running multiple sets of the same data or similar data through a similar model architecture with all the other parameters the same and only changing the learning rate. So it turns out to be a lot of work, right? And this is also not surprising why AutoML typically takes a long time to train. For any simple, like very simple problem, even if it's a problem that's basically trivial, it doesn't necessarily require machine learning, you could do with a simple regression model. If you use AutoML, it's going to take probably an hour or more, just because how much infrastructure is required and how much it takes for things to get loaded up, the pipelines to get deployed and all of that. So when should you consider using AutoML? Oh, and this is another dimension that sometimes you have to think about when you get hit with an exam question, right? And that is like the readiness and the current stage of this like use case or this company. So AutoML is typically very good for teams that are less ML mature, teams that are building features and products that don't require machine learning as a core competitive advantage, right? So it's easy. You're like, okay, we have some data. We're gonna just give it to AutoML and Vertex AI, and we'll see what comes out. And if the final version is good, then we'll use it. We'll treat it like a black box, all of which you can do, using Google products. And that's that, right? It is not very suitable for people who have machine learning capabilities or are very specific about how they want a model to behave and how the model should perform in terms of speed, latency, or accuracy and things like that. It is also more expensive if you do AutoML, right? So with that kind of like tangent, we talked about learning rate as a very good example of a hyperparameter, but guess what? Like things like even model structure could be a kind of a hyperparameter that you tune in a way, right? Or the optimizer you use in your like gradient descent. Sorry, the optimizer you use in your deep learning in your training process. So here is kind of describing what learning rate does. I think we have already went over this like probably 2-3 times. And the key thing here is that, okay, we know what a small learning rate does. When we know what a big learning rate does, then how do we choose the right one? How do we know what case it is in, right? If people want to review, we can go over that again. But I feel like everyone probably has heard this many times, and so I won't spend too much time on that. Okay, so then we are going to kind of go over everything we covered. And this is where, like, Roya, especially for the earlier weeks, if you feel like there's a key point that, students should consider, definitely feel free to chime in. So we'll just do this part collaboratively, right? First thing you should understand is the ML problem framing. And once again, this is one of those things that I mentioned is like a multi-step process. And once you understand the framework, it will help you solve the rest of your problems, right? A number of questions we've covered and a number of questions we will see are of the type that this is the actual case. It will give you a few like tidbits about, oh, if you should, trigger or bring this thing about, oh, this is about inference speed, or, oh, I want to reduce cost, or, oh, this is a new team, and they don't know too much about machine learning. So if you understand ML problem framing, this will help a lot with like eliminating a lot of options for those like use case type questions. So usually what this whole thing comes down to is actually who should we talk to and what are their requirements and what data do you need, right? And specifically, what does your label data look like? So if you can answer those questions, then you can essentially then pick a good ML metric that maps as closely as possible to your business outcome, right? And then you will determine a threshold level before you even start doing any machine learning training with your stakeholder to say, okay, so if we decide to use this metric for a classification, maybe it's F1, we are okay with deploying. If it's above 65%, we're real happy if it's above 80, right? We're not going to consider anything deploying if it's like less than, whatever, then everyone's going to be honest and everyone has a very tangible plan to discuss like what to do down the road, right? So once again, this part is about make sure you understand how Google wants you to think about a machine learning problem, how to frame it, understand like what exactly is the business objective, who are the stakeholders, what does the data need to look like, and what does the label mean in the context of your data? Because most of our learning has been supervised so far, right? That requires label, and then mapping that business requirement to an ML metric. So, for example, going back to the recommender example, if the business requirement from the product manager is like, I want as many new monthly subscribers as possible because they pay, like $8 per month, then your metric may be, okay, what is the like conversion rate, right? I want to maximize conversion rates. So that is that. One of the key things that's important here practically if you're doing like machine learning in production is that you want to get a gut check from your domain experts, right? So the questions I like to ask for that step is, okay, so if I were to give you this task and you're a reasonable human, what is your expected performance? And if I give this, task and the same data to a domain expert, what is their expected performance, right? And also, what are the key things you would look for in the data to help you make that decision? If you can only ask for one piece of information, what would it be? If you can ask for a second piece of information, what would it be? What would it be, right? Because what you're doing is essentially doing feature engineering with a domain expert, which helps a lot. So that's kind of about the framing part. So then it's important for you to immediately map that to a like high-level architecture, right? What are the kind of chunks you're going to need in this machine learning pipeline? What are the options and what are the horse trading pros and cons for each of the options, right? So for example, for the model training and serving step, you can use Vertex AI. The benefits are it's low maintenance, but it's expensive. Or you can choose the self-managed option by clubbing together, TFX of pipelines, adding your orchestrators, deploying your own Kubeflow orchestration, all of that stuff, right? So that would be a good example of the architecture and trade-offs you have to make. So yeah, and then one of the key things here is understanding the difference between CPU, GPUs, and TPUs and when you should be using which, right? And because we're also talking about hardware, it's either here or somewhere else where you have to really understand the distribution strategy. That I guarantee you that question will show up on the test, and if I'm wrong, I'll give you $2. But yeah, that is assuming we all take the same version of the test. Otherwise, who knows? Okay, so week 3, this is where we kind of have a container or playground for your machine learning to happen. You talk to your data engineers that are getting that worked out, or maybe building you some pipelines. You have some data to start, going through the iteration process. So this is where the fun kind of happens, right? It's this is where the fun starts. So first of all, you need to get the data into where you're going to be working with it. So that's data ingest. And these are the common steps for no matter what products you use, AWS, GCP, Microsoft Azure, whichever other ones. You can even clip together different ones. And then once you are able to load the data, then you want to do some exploratory data analysis, EDA, right? And like Roy has said many times before, the more time you spend on EDA, the better your projects will become. In fact, if there's only one factor that I choose to be the most predictive factor for how well your ML works out, is how much time and how much effort and how much critical thinking you spend in this EDA process, right? So don't rush to the modeling stuff. The next thing you want to do is, after you know what your data looks like, you want to design your data pipeline, right? So this typically, if you're working with the TensorFlow ecosystem or the Google Cloud ecosystem, probably involves TensorFlow data validation. You're probably storing the data somewhere on Google Cloud somewhere. If it's structured tabular data, maybe use BigQuery, right? You can also use Google Cloud storage buckets. If it's unstructured and more like files, then probably use Google Cloud storage buckets. And then a key part of this is also the transforms, right? How do you take the data and reliably and scalably convert it into a format that your model can actually eat, right? Because if you feed your model garbage that's not cleaned and transformed, you're gonna get kind of really bad results anyways. So don't spend that time and don't waste that money. And then once you're able to do the transforms using one of the TensorFlow product offerings, then you can do a little feature engineering, asking which features do I think will be most useful for the model, right? As you know, the more data you add or the more feature you add, you typically can only improve your model, but also you may hurt your in production result by reducing the generalization, because you're now overfitting, right? So that's what feature engineering is for. So if you're doing feature engineering, you can use something like a feature store, but it's not strictly required. So week 4, this is where the kind of what we consider the fun stuff. But to be honest, the fun stuff is now just table stakes, right? Most people can spin up a Jupyter notebook or use Google Colab, run some code. Even if they don't know what the code does, they just copy pasted it, apply it to some data, and get a working model. And usually it's pretty good, because we're now in the age of commodified foundational models, right? So this is the fun part, but this is now table stakes. What actually distinguishes you as a company or as a individual in this market is ML ops and DevOps, right? And also your data food, your data skills. So what is actually involved in this step? The core ML is building a model, training a model, testing it, and then making the results available, right? And this is typically a very iterative process. Some practical advice I can give you: when you're building a model, I typically like to have a set of 4. One is just the most baseline, most simple model, right? And then that's just to keep myself honest. If the other models are doing great, but then a very simple model is doing not that much worse, then am I really doing my job as a deep learning engineer, or could I just use something easier, right? So I use a very simple baseline. Usually it's a gradient boosted tree of some kind, because they actually have comparable representation power to neural networks, like deep dense neural networks, but they're easier to train and more interpretable, right? So either a regression model or a boosted tree model, and then I'll use 1 or 2 state-of-the-art model. These are mostly for my own purposes and for my own learning. I want to experiment and see how they perform on different sets of data, and then I'll choose 1 or 2. Depending on the nature of the project. If it's more researchy, then I'll choose state-of-the-art techniques. If it's more production-oriented, closer to production in terms of stage, then I'll use 2 kind of more production-oriented models, right? And these are models that I expect to behave very well in production, easy to debug, easy to kind of monitor, and those kind of things, and also fast, right? Fast to train, fast for inference. So once I define the set of 4 models, then I kind of parallel train all of them, right? And if there's one that I want to specifically work on or tune, then I'll kind of pause everything else and do that one. And then afterwards, you come to the stage of okay, we have some ideas, we have models, which one do we want to use? And this is where defining your machine learning metric is very important, because that is the thing the ML model will try to learn. And if you give it the wrong target, it won't be able to help you with whatever you're trying to make it do, right? And also choosing the wrong metrics for a model may lead you to deploy a model that doesn't actually very well match with what the business objective is, right? So choose your metrics extremely carefully. Understand the finer details of trade-offs will be important, right? So to answer this question, first of all, you need to know, are you doing a classification kind of problem, or are you doing regression kind of problem? And even within regression, there's a number of essentially distance metrics that you can use to calculate the error. And when I say distance and error, sometimes I use it interchangeably, because in the work of machine learning, you're trying to reduce the distance between your prediction and whatever your actual data label is, right? So know when you should be using which error metrics even within these buckets. And then finally, scaling and training and serving. So this is where the framework comes in handy again. So for example, to survey, a model, you can potentially use BigQuery ML, you can use Vertex AI endpoints, you can use AI platform endpoints, which I haven't really played around with much, because I didn't use Google Cloud as a main tool before, and when I started to use it, Vertex AI hard. But just know how you make those choices. And understanding if you're trying to optimize for speed doing training versus speed doing inference, those are two different things, right? Okay, so week 5 and week 6 is honestly where the core and the meat of the courses, and what I also expect to be heavily tested on the exam. Because let's think about, why did Google design the certification, right? This is marketing and also upskilling 2-in-1, right? Why are they providing these free credits for you to go through this? Well, they're also trying to make you learn their products, right? So it is very much expected that you know how to work with Google products, and not just know general machine learning. So same steps, but now it's more focused on which tools out of the tool set that Google offers you should use, right? So I've been kind of blabbering for a while now. I want to go to the chat and see if people have questions. Oh, okay. Thank you, Roya. That's very nice of you, but definitely feel free to pause me at any time. Yeah. Okay, and if people have questions, I should mention that there is a Q&A tab. So it's the second row of horizontal bars in the chat panel. If you have questions, feel free to add it in there so I don't miss any of them. And if there's a lot of questions, then people can upvote, downvote on the questions that they care the most about, so we can prioritize. So since there are no questions, I will go back to the slides. Let me share this again. Why do you look like this? Okay. Okay, so one thing that I want to mention here that's very important is this idea of monitoring, right? This idea of training, serving skew. So that's another question I'm willing to bet will show up on the test. So these are kind of the more practical considerations that you need to start to worry about, right? One of the key things you can do is having a transform function that you can compose and click together, kind of the way Lego blocks fit together, is that you can use the same transforms for how you process the training data and how you process the test data, right? So let's say you're doing something like a normalization, and I mentioned that normalization for most machine learning is a good idea. Why? It saves your model from having to learn the statistical distribution of a certain, for example, continuous, feature, right? It's not categorical. So you're getting smooth value, maybe 10.01 or 11.5 or something like that, right? So normalizing that as a pre-processing is usually a good idea. Because if you don't, your neural network is going to have to spend a few nodes or a few layers to figure out, oh, okay, this is the data I'm getting. Apparently, it's people's heights in centimeters, and the mean is around 150 centimeters, and then the variance standard deviation is around 20 centimeters. I think that's wrong, but you get the idea. So if instead of making your model learn that by itself, using its own nodes, if you just do that work like with precision beforehand, then your model can actually use those kind of like parameters to learn something that's less obvious, right? So if you're lazy, your model's gonna have to do more hard work. But then so like try to help it out as much as possible. So in the way that Google likes to think about machine learning, I'm starting to see that there's a few things they talk about, right? One is the artifact, which is for each of these transforms or the functions that you can call repeatedly as a piece of code you can run as a piece of the pipeline. You can run in a container. What is the output, and how do you what information do you need to log in the output so it can be reproducible, scalable, and then mix and match different components, right? You can have model version 2 but running pre-processing function for normalization version 5, right? So that's one of the key, I guess, selling points of using a managed service platform like Google Vertex AI, because everything has the right I guess interfaces to clip together. So that makes your job pretty nice and pretty easy. So the more information you log, the easier it is for you to do your work as a ML person, either by running experiments, doing hyperparameter tuning, debugging, right? Or which data sets did I feed into the model that caused the improvement or degradation? And specifically, what was the actual example that broke the model or something like that, right? Okay, so this stuff honestly is hard to learn without actual experience. One thing I would recommend is take one of the kind of foundational models available on Hugging Face, or what Google calls their model garden. Take one of those models and productionize it, right? So you can take for example, image generation model, and then write a very small, maybe 2-3 function pipeline, and then deploy it using Vertex pipeline or whatever tool you want to use. Add a orchestrator to trigger retraining. Make sure you're able to look at the train test skew, and then artificially putting some data that's outside of your training distribution, right? So you take a very small example and then go through every single step. So that way, with very few actual projects, you can map exactly what step you're in and what are the tools that are available and what are the key trade-offs. And that way, it's probably the most efficient way, at least for someone like me who learns the most from doing, in terms of remembering these things and how to reproduce good answers on a test, right? Memorization almost never works for me because I have dyslexia and I usually almost always remember things the wrong way. Okay, so ML solution monitoring, optimization, maintenance. This is the second half after your model gets deployed. So how do you know something is bad, right? First question, that's ML monitoring, right? Second question is, how do you know what made it bad and why it's bad, right? So that's kind of troubleshooting. So back to the idea of metadata, tracking lineage, producing artifacts. The more artifacts you can produce, the easier it is for you when you need to make these improvements, because you're just really helping yourself out, right? There's nothing worse than a model behaving badly in production and everyone's yelling at you or very stressed out about it, and you're like, I don't know why, because I didn't spend the time to add logs or anything like that. Okay, and then tune performance of ML solution for training and serving production. This is I'm not 100% sure what they mean here. Roya, do you know? I can look it up and get back to you, but
I think Roya has some problems with her mic.
Oh, okay.
I'm not sure.
Yeah, maybe Roya can add a comment or something, but I'll circle back to it. What I read that as is oops, we cannot be showing sample questions yet. It's to understand your training and your production may have different demands and services. And so I was like, oh yeah, make sure you do the same normalization, right? So that actually means if your production data is expected to be from the same data generating distribution as your training data, then let's say you kind of did clipping with a norm or a mean of 5 and then a standard deviation of 1, you want to apply the same clipping and the same normalization to your production data, right? That's typically how I've seen it done, how it's recommended, even if your production has a slightly higher mean or slightly lower variance or something like that, right? So if you're going to apply the same transforms, then the question becomes like, how do you know if there is a actual problem, right? So all of those things are like the monitoring, optimization, and maintenance step. So almost everyone can get a model deployed into production, right? It's pretty easy now. So the companies and the teams that get a competitive advantage are the people that notice problems earlier, have enough data logs so they know how to form hypotheses for what these problems are. People who are able to run efficient experiments and parallelized experiments using distribution strategies, probably, to figure out what exactly is the fix for the problem, and then do a safe redeployment, right? So the quicker you can go through that cycle with CI/CD, the faster you can get ahead. And with everyone starting with foundational models, this is a very critical thing. Especially for those who are like, building their own teams, running their own teams, or like trying to start a company. So CI/CD stands for continuous integration, and CD actually has two different versions: continuous delivery and continuous, I think, deployment. There's also continuous training, right? So make sure you learn and understand the difference between all these concepts. Okay, so long slide. I guess week 6 doesn't count because we're not covering any actual material. Okay, so that is all I wanted to say about this. Let's check the chat real quick. Oh, awesome. Okay, so thank you for confirming that, Roya. All right. Oh, someone's asking the 4 types of model I use. So actually, there's really 3 types. And I don't always do this, but usually I end up doing this for like a properly spec'd and properly like resource project, right? So one is like state-of-the-art model. Sometimes I'll have one of those in the mix. Sometimes I'll have 2, and then depending on like nature of the project and timelines. If it's like more researchy and more like I have a longer runway before engineers need to be like, hey, where's that model we're gonna need, right? Then I will probably try 1 or 2 like state-of-the-art models, because that's a way for me to learn and a way for me to take that learning back to other projects and also to my team, right? So 1 or 2 state-of-the-art models, what I call SOTA, 1 or 2 most likely to be deployed models, and then 1 like baseline model, right? So the baseline models, there's 2 that I typically default to. 1 is a regression model, just a straight up linear regression, right? And when I say linear, it actually like is polynomial as well. So for example, like, x to the power of 2 plus x plus, a times x to the power 2 plus, b times x plus, c to the, x to the power of 4, right? So that is also a regression model, right? It's not linear because you have exponential terms, but because the terms are linear in themselves, it functions like a regression model. It's fast, fairly, explainable, all of that, right? So there will be one of these, and also a XG boost or like gradient boosted tree model. So gradient boosted trees are both for regression and also for classification, right? So the regression model basically works the same way as a classification model, except how they give you the output. For a classification model, the idea is that, have people seen that game where you drop a pinball and then it's bouncing around a bunch of pins and in the end you're landing a bucket, right? That's exactly how that model works. It's gonna basically decide one or another branch to go down the tree, and it's gonna landing a bucket. For the classification case, you're hoping that the final buckets are similar within themselves and then different between the buckets, right? So, and then if you're doing regression, what you do is after you make sure the items or the data points that land into each of the individual like buckets at the bottom of the tree are similar within themselves and then different between buckets, then you basically take the average of that group, right? So one concrete example is like, I cannot think of a good example of doing this without getting myself into trouble. So let me think about this a little bit carefully here. So let's say we're building a classifier for on the iris data set, right? There's some information about a flower. You're trying to figure out what kind of like flower it is. So maybe it's looking at the length of the petals compared to the radius of the center, whatever that round thing is. And then it's able to kind of like correctly bucket iris type 1 into the first one, and iris type 2 into second one, type 3 and type 4. And maybe because everything in the first bucket is iris type 1, so they're similar within that bucket, but they're different compared to iris type 3, right? So you understand that. So great, we have a good classification model. Then how do we use this model for prediction? Well, let me change the problem to predicting the I don't know, the height of this flower, right? So then you basically take everything in that first bucket, which is predominantly iris type 1, and then you average them and you predict their average height. So that's how you go from a boosted tree models to do both classification and regression. And you don't need to do the classification first before you do the regression, right? So that's kind of like a very long explanation of the set of models I like to use, and I like to make sure I have. So then the question is how I would actually use this at the end, right? So frequently the state-of-the-art model will be better, but necessarily the model I would deploy if it's not like better by far, right? Because other considerations you have to keep in mind: how long is it going to take to retrain the model? How much data does it take to update? Is it explainable, right? Is it going to scare people? Because some people are still a little bit like unsure about how to feel about neural networks. So it's like harder for them to understand than a regression model. So there is that. Okay, so unless there are other questions, we can switch to some sample questions. And then I'll cover the pipeline stuff a little bit later. Okay, so are we? Yeah, I think we're sharing screen still. Okay, let me actually share my screen. I am not sharing my screen. Okay. All right, so I will let folks read this question, and I will read the question as well. And I want to see votes in the chat. So the question goes: you need to build a object detection model for a small startup to identify if and where the company's logo shows up in an image. So you were given a large repository of images, some with logos and some without. These images are not yet labeled. So you need to label these pictures and then train and deploy the model. What should you do, right? So the question is really asking a few things, like how do you get label data? Because that's one of the key things you have to think about in ML framing process. And then it's also testing how well you know Google products. For example, what is the capability of AutoML object detection, right? Is it likely to know what your small startup's logo looks like? Or is it, more able to pick up something like, Google's logo because Google's more popular, right? So those are some of the things I look at. And then anything that mentions manually doing anything, then you're like, well, am I saving enough money for that manual work to be worthwhile, right? That's the question you ask. So I'm curious to see what people ended up voting on. Yeah, lots of A's. Awesome. Yes, pay your kids. Although if your kids are smart, they would use AutoML. Yeah. Yeah, okay, so this is, I actually had a little hesitation about the AutoML part, and now I remember that we are actually getting label data, so that's good. Okay, so why is A the right choice, right? AutoML doesn't take a lot of label data to learn something. So if you're able to get label data by using a Google service, then that's good. So why is B not correct? So Vision API, like I mentioned, probably doesn't know your startup or its logo. So you can't use it as a labeling service yet. So the next two sounds very painful, so usually that's wrong. If you're an engineer and something sounds painful, it's probably not the right answer. Okay, so next question. So far, everyone that's answered is 100% passing, so that's good. You work for a textile manufacturer and have been asked to build a model to detect and classify fabric defects. You train the machine learning model with a high recall based on high resolution images taken at the end of the production line. You want quality control inspectors to gain trust in your model. Which technique should you use to understand the rationale of your classifier? So your options are K-fold, integrated gradients, PCA, which stands for principal component analysis, and K-means. And K-fold stands for K-fold cross-validation. So yeah, let's hear some votes or look at some votes. I see a B. Anybody else? Anybody else? No? Okay, yeah, it is B, and this one's pretty simple because it's about trust. It's usually interpretation and things like that, right? So it's B, good. So again, 100% pass rate. So this one is a little bit interesting. You need to write a generic test to verify a dense neural network model automatically released by your team have a sufficient number of parameters to learn a task for which they're built. What would you do? So first option is train for a few iterations and check for NaN values. B is train for a few iterations and verify the loss is constant. C, train a simple linear model and determine if the DNN model outperforms it. And last one, train the model with no regularization and verify the loss function is close to 0. So this one is actually a little interesting because this doesn't necessarily test your Google product knowledge, but it tests your your experience and in-depth understanding of neural networks. So let's hear some votes. There's a couple B's and a couple D's. Okay, cool. So the answer is D. But C is something I just said I do, and I'll explain to you why that's wrong in this context, and I'll also explain why A and B are incorrect. Let me actually double check. Good. Okay, so train a model for a few iterations and check for NA values. You could have checked for NA values before you train for a few iterations, so yeah, that was basically incorrect. The next one says train for a few iterations and check that the loss is constant. This is a test to verify that you have a bug in your code. This is one of my favorite tests, right? If I train a few iterations and the loss is noisy or nothing's happening, that means I have a bug in my code, and I basically stop training immediately, right? It's a very quick test that it's a necessary but insufficient test to determine if you're ready to kick off some large-scale training, right? If it doesn't even pass that test, it's not decreasing the loss on the training set, you have a bug, don't even proceed any further. C, train a simple linear model and determine if the DNN outperforms it. This is literally what I just said I like to do for the set of 4 models or set of 3 types of model I like to use. So why is it incorrect here? The goal of that is to do final model selection, right? The goal of this is to see if your neural network has enough capacity. Just because it is able to beat a linear model, simple linear model, doesn't mean it has enough capacity. Because maybe if you added 4 more layers and 20 billion parameters, it's actually able to improve your your accuracy from like 70% to 90%. Just because it's better than some other model doesn't mean you're doing a good job with your current model structure, right? So that really leaves the last one, and I'll explain how this works, right? So in the old days, before compute was extremely cheap, there's a school of thought that says you have to like kind of size your model appropriately. You don't want it to be so large that you later have to regularize everything, right? Which you can do. And you don't want to be so small that it's not learning the things you want it to learn, right? But now that compute is very cheap, and also Google wants you to pay for compute, a simple way of doing this is like overkill on the model capacity by adding a good number of layers and a good number of parameters for each layer, and then train the model on a very small data set, a very small randomly sampled data set, and make sure it's able to essentially memorize all the patterns, right? And then you can apply regularization. So regularization, including dropout, L2, L1, or even quantization. Those are all ways you can regularize a neural network model, right? So, okay, so that's an interesting one. We'll spend a little more time on it. So this one's also interesting. Your team is using a TensorFlow Inception 3 CNN model. That's a convolutional neural net. So it's pre-trained on ImageNet for image classification prediction challenge on 10,000 images. You will use AI platform, or we can just read that as Vertex AI, to perform the model training. What TensorFlow distribution strategy and AI platform training job configuration should you use to train the model to optimize for wall clock, right? That's literally training speed. So 4 options here. One is use default with master node and 4 GPUs. The next one is one device strategy with, one says 4 GPUs and one says 8 GPUs. And the last one is mirror strategy, single node with 4 GPUs, right? So when I look at this question, exam strategy kicks in. So does 4 versus 8 GPUs matter? If it does, then definitely use 8. And then the other question is like A versus D, right? Which one is it? So that's kind of like my first read on the question. So I'm curious to get some votes. Okay, what's the difference between A and B? 5 seconds ago? That's probably this one. Okay. So default strategy versus one device strategy. That is the main difference. I'm actually not sure if one device strategy is a strategy. I haven't encountered it that often. I misread it many times as on-device strategy. So, any votes? Votes. Christopher is asking, we're trying to minimize storage, correct? That is incorrect, because the question is saying we are trying to optimize for wall clock time. As in, money is not a problem. You can use whatever architecture you would like, and you just want this to get done fast. And you're trying to optimize for training, right? Remember, like thinking about the ML framework. Do I care about inference, or do I care about training? What is the bottleneck? Am I bottlenecked by the communication, or by the data, or is it the model size that's too large, right? So these are the questions you should ask yourself when you're trying to figure out what is the distribution strategy. Add ray.io. Yeah, okay, awesome. Between you and me, William, I also like Ray a lot, but until Ray has a certified whatever professional ML engineer thing, we have to see what Google likes. Any other votes? No votes. Okay, so answer is D, right? So let me actually make sure that is, yeah, answer is D. That's good. So let's go through why, right? Default strategy. This is the null case, or the no op case of a distribution strategy. It has the exact same shape and the interface as a distribution strategy, but it has no actual substance. Why would Google do this? It is because sometimes you want to keep your code the same and just change the variable of the distribution strategy. Let's say you're training locally, you're trying to run some like very quick test, or you're trying to do like a local prediction or something like that, just to see a debug very specific case. versus you're deploying this to like multiple endpoints, right? I know this is training, but I'm kind of like going over why they might have implemented like this. So the default strategy actually doesn't do any distributed training at all. So that's also the problem with the one device strategy, right? One device strategy also does not do any distributed training. So really, based on that alone, you should know the option is the mirror strategy, right? So now, when I look at this question, I almost immediately eliminated B and C, even without knowing, like, even when I misread one device strategy is on device strategy. Why? Because there are just too many like options involving how many GPUs, right? And sometimes when a question presents you options like that, it's like, okay, 2 options from this category of choice, as in what distribution strategy, and then 3 different choices from how many GPUs you should use. Sometimes a part of the question is actually a moot point, as in it doesn't matter at all. And this is classically one case where that would show up, right? So because everyone's like the number of GPUs, immediately as a person who's very well trained on doing multiple tests, I'm like, that's probably not what the problem is. So I just focus on the first part. So hopefully that helps in terms of like multiple choice test taking. Okay, this one is really important, which is the thing I talked about, which is how do you evaluate machine learning models, right? So you work for a maintenance company and have built and trained a deep learning model that identifies defects based on thermal images of underground electric cables. Your dataset contains 10,000 images, 100 of which has visible defects. How do you evaluate the performance of this model on a test dataset, right? The options are area under the curve, AUC, calculate the number of true positives, calculate the models to have like actual visible defects, and then also the last option is calculate cosine similarity on the test set and compare it to the training set. So a few things immediately popped into my head as I'm reading the question. So first of all, there's a train test set, so that's good. Second of all, this is underground electric cables. I don't know about you, but I feel like this is a fairly expensive mistake, right? So I don't want to make false positive mistakes. As in, I'm like, oh yeah, this cable definitely probably has a problem. I dig it up, it has no problems. I think someone will be very mad at me. It also has 10,000 images, so that's not a ton, but it's like sizable, right? So, but that doesn't matter for this question. It's simply about how you evaluate this. So, any takers here? This is a pretty easy one. Oh, we have a good number of distribution here. We have some A, we have a D, and then C. Okay, so how do we figure? Okay, so let me shoot down the ones that I know for sure isn't correct. So I'm gonna pretend I'm actually doing this question on a test, and I'm gonna walk you through what I'm thinking, right? So D is not correct because this question mostly cares about how well you're doing on the evaluation set, the test set, right? We're not really worried about overfitting, underfitting here. And that's where comparing the performance on the test set versus the training set will be the most useful, right? Also, cosine similarity, to a model performance, I don't even know how they want you to do that, right? So D is a bunch of gibberish and doesn't make sense. So the B and C have a very similar taste, and that is it's calculating one side of the accuracy, right? So you can either have very low false positives and you can have very low false negatives, but then the other side suffers, right? So let's use a case. Maybe you're trying to do a blood test to detect some kind of like terrible childhood cancer, and the test obviously sometimes false positive, sometimes false negative, right? And if you happen to detect this cancer, there is a low risk vaccine you can give that basically fixes the problem. So in that case, it's very costly if you're wrong, because then some poor kid has cancer and then doesn't know about it. But then if you make a false positive, as you're like, oh, this kid may have cancer, the error isn't as bad, because I just mentioned there is a low risk vaccine that would fix the problem, right? Obviously, the right answer is to do another test, but given those cases, you would want to lower your false negatives, right? False positives aren't as bad. And then there's the other case of, you're trying to like predict your whole citizen population, which one's going to be a pirate, right? Obviously, most people in the population is not a pirate. So if you just take, your whole like census data and you train, the model's probably going to be like, nobody's a pirate. But then pirates could be very, very bad, very damaging to society, right? So you don't want that many but at the same time, you don't want to like mistakenly send someone to jail when they're falsely predicted to be a pirate, right? So that's when false positives are bad, right? So basically, the whole key here is for classification, you can't look at things once that you need a combined metric. So F1 is a good way of doing that, and so is area under the curve, right? When you look at the calculation for F1 and also the calculation for AUC, you'll see these terms show up again and again. One's false positive rate, one's false negative rate, which we just talked about, and also the terms true positive, true negative, right? So I can send people some articles about this, but this is like super critical to understand. You need to know the key metrics you can use to evaluate a regression model, and they behave differently. For example, some are more sensitive to scale, some are more sensitive to variance and things like that. And also you need to be able to make the right decision for classification. And just because I typically harp on using like a balanced metric for classification, make sure you capture both the false. Sometimes that's not the case. For example, in that like childhood cancer detection case, that's a trick question, right? If you always think, oh, classification must be balanced metric, you choose F1 or AUC, then you would have lost a mark there. So nothing's always the case. This may be the last question, but let's move on to the new one here. So this one is also very simple. You're working for a large financial institution that's planning to use Dialogflow to create a chatbot for the company's mobile app. You have reviewed old chat logs and tagged each conversation for intent based on each customer stating intent for contacting customer service. Okay, so basically you have label data. About 70% of the customers' inquiries are simple requests that are solved within 10 intents. The remaining 30% require much longer and more complicated requests. What should you automate first, right? So choice A, automate a blend of the shortest and longest intent to be representative of all intents. Okay, this is a good sampling technique. Cool. Option B is automate the more complicated requests first, because those take more of the agent's time. Option C, automate the 10 intents or the 10 different like cases or tags that cover 70% of the request, so the live agents can handle more of the complicated requests. And last option, basically use a heuristic. So it's saying automate intents in place where common words such as payment only appear once to avoid confusing the software. Okay, so let's get some votes for this one. Oh, this one's universally C. Let's see if that's correct. All right, let's see. Yay, we all passed. Good. So this is classically the 80-20 rule, right? So usually 80% of the resources are spent solving 20% of the problems. So that's where you have the best bang for buck, right? Another way to think about this, and this once again goes back to the high-level frameworks, is like Google's principles for machine learning, right? One of the key principles, I don't know how they said it, but this is common for a lot of ML principles, is that you should make the ML augment and assist humans and not make the ML replace humans, right? So C is, that case, because you're automating a lot of the boring tasks and you're letting the humans handle what they can deal with best, which is complexity, right? So these agents can, ideally spend more of their time on the complicated cases, not just, send people PDFs that they need to print or whatever. And this is also a very effective way to reduce costs, right? But to be honest, a lot of times, jobs will be impacted. So it's not always perfect. So this last question, I think we've seen it a couple of times. So I'm testing memorization, but also I want to walk through this question because this is a very good question, right? So you work for a gaming company that develops and manages a popular, massively multiplayer online game. The game's environment is open-ended, and a large number of positions and moves can be taken by a player. Your team has developed a ML model with TensorFlow that predicts the next move of each player. You cannot do edge deployment, which means you deploy it onto the user's device, but you do require low latency serving. So how should you configure the deployment? So, here are the options. Use a cloud TPU to optimize model training speed. Use AI platform prediction with an NVIDIA GPU to make real-time predictions. Use AI platform predictions, which is, AI, Vertex AI, like serving endpoint, basically, with a high CPU machine type to get a batch prediction for the players. Or the last option D, use AI platform prediction with high memory machine type to get a batch prediction for the players. So this is a very good question because it's very subtle about the key points, right? So I'll once again have you vote, but also verbally tell you what I see when I see this question. So first of all, environment is open-ended. There's a large number of positions and moves possible, right? So immediately I'm like, okay, this is going to be a very busy endpoint. Why? Because there's a massively multiplayer online, a lot of players, and for each player we have to make a prediction, which means the model output probably is a softmax with a high dimension, right? So if we remember, softmax is basically predicting the probability for each category, right? For example, what is the next word, which is also similar to this one. What is the next move taken by a player, right? So also they don't care about training. This is all about low latency serving, right? So immediately the first answer, use a cloud TPU to optimize training speed, irrelevant, immediately wrong, right? So then it's throwing in a couple keywords which may be confusing and may sound right. One is saying use a high CPU machine to get a batch prediction for the players. The next one is use a high memory machine to get a batch prediction for the players. This is once again one of the setups of multiple choice questions where they're trying to distract you, right? The common part is the batch prediction, and that is wrong because if you're doing batch predictions, it is not going to be low latency. So let me briefly explain how that works, right? So batch prediction is maybe cost savings for compute and makes it easier for you to do model management, and that requires basically collecting a bunch of data that you prediction from, and then when you have enough cases you want to predict, you call the API at the same time with all the data, and then you get all the results back at the same time, right? It doesn't sound like that's the case because each player could require a different next predicted move at any given time. So this batching immediately doesn't work. So that leaves us with option B, right? But I like how they're throwing in, do you have a memory constraint or do you have a processing speed constraint, right? So high memory is typically when you would need to use the TPU, right? That's usually the case when you have a very large model with a lot of weights. And also because it has a lot of weights, it's going to need a lot of data to update the weights, right? So that's when I typically would use a use a TPU instead of GPU. And I think I saw a question previously that's a perfect thing to mention here. I think Christopher asked, is distributed training faster than local always? Yes and no. In most cases, yes, because you simply have more like parallel links, right? You go to post office, there's only one person at the counter. Wow, that's going to be really slow. If you have three, then that's good. But sometimes it takes time for all three of them to boot up, right? Then in those cases, you might be good with just one line, right? So let's say the setup at the post office is that all three of them start at the same time. All three of them need to have their computers ready, their software booted before they can serve anyone, and there's only one person waiting in line. Well, guess what? if one computer is having a bad day, or Windows decides to update software like surprisingly at the beginning of the day, well, that person actually would have been better off with just one window open, right? So in those cases, distributed training doesn't make any sense. So then between the two distributed training strategies, which I predict to be on the test, how do you choose which one you want to use? There's the parameter server option, and there's the mirror strategy option, right? So parameter server, once again, is when it's constrained by essentially the different rounds that the devices have to go through, right? And the kind of like mirror strategy option is really good when you don't want to, when you don't have like as many different kind of like device capacity, and you're kind of more limited by the network communications, right? So that's how you kind of like make that trade-off. So yeah, so by the way, I think NVIDIA might be the only GPU that Google Cloud has decided to work with, but I may be wrong about that. So usually I've only seen NVIDIA mentioned. And actually, I lied. There's one last question, but we talked about this many times, which is you're working for a large retailer. You want to use ML to forecast future sales, leverage 10 years of historical data. You want to rapidly experiment with all available data. How would you build and train your model for the sales forecast? So this question, it mentions BigQuery and using the RIMA model, and then BigQuery, and then using BigQuery ML. Another option is to use CSV and create a regression model on AutoML tables. Another option is to convert into TF records and use RNN. Another option is to change the data into CSV again and using XGBoost, which is a gradient boosted tree model by platform training, which is Vertex AI essentially. So this question, it tests you both understanding of the product, as in what format you should use. Is it CSV, is it BigQuery, is TensorFlow records? And also what model is most likely suitable for this question, right? So remember, there's really two things they're testing for: your foundational machine learning knowledge and also Google product. This is a combination of the two. So if you suck at one of them, hopefully you can, use testing strategies to figure out, right? So CSV is not the way to go because it's slow, right? RNN is not the way to go because that's likely overkill for this kind of problem. And XGBoost is a tree-based model, which means it's unlikely to perform well with out-of-sample distributions, right? But as things like of a time series nature, it's entirely possible that inflation keeps going up, right? So it's not unlikely to expect to see data that's coming out like from a slightly different distribution as you're deploying this model into production. So that's how I would go about answering this question. Oh, actually, I lied again. There's one more question. So you're a ML engineer at a media company. You want to use machine learning to analyze video content, identify objects, and alert users if there is inappropriate content. Which Google Cloud product do you want to use for this project? So first of all, PubSub is the first option. So clearly it's PubSub. But also anytime you see anything related to streaming, that's the first thing I think about is PubSub, right? And then the next one you're trying to figure out is what API you should be using. Because cloud logging sounds like it's also pretty important because that's how you're going to use the log to trigger a user and send them an email, right? So basically it's what's in the middle. Is it cloud functions? Is it cloud IoT? Is it data flow? Is it cloud vision API? Is it video intelligence API? So what it comes down to is the fact that this is a fairly common use case. Therefore, it would make sense for Google to have a standard model for that domain, right? So Google has foundational models that have a certain structure. For example, large language models in the form of transformers like BARD, like POM or Bison or something like that. It also has domain-specific models. So, for example, language model adapted for finance, for retail, right? So in this question, it is the video intelligence API, because I know that actually is a product I'm pretty sure, right? So actually, let's double check the answer before I lie. Yeah, okay, so it is a product. So because this is video and I'm using an API, I'm not doing any custom model training, I'm gonna choose that one because it's the closest to my use case, right? So then you're like, okay, Maddie, why is it not AutoML video intelligence? Well, AutoML, the key thing is you still need labeled data, right? So it doesn't say that you have labeled data. It's just doing prediction at this point. So you have nothing to really train on. Therefore, you can't really use AutoML video intelligence. And also, if this is already existing, why would you, basically train a custom version of something you already have, right? So that's also why D is not an option. Wow, there's way more questions than I remember. So last question, hopefully, is this last one? Okay, yeah, it is last one. Okay. You're on a team where you're processing. You're in the process of deploying a model into production, and it starts with data scientists training different version of the model on Kubeflow pipeline, which now is basically a self-managed version of Vertex AI pipeline. The workflow then stores the new model artifacts in Google Cloud Bucket. You need to build the next step of the pipeline after the submitted model is ready to be tested and deployed in production on the AI platform, which I'm just going to read as Vertex AI. How should you configure the architecture before deploying the model to production? So basically, what this is testing you is, should you deploy and then evaluate and then make a model version, or what is the order in which you should do that, right? So this one is, the answer is actually A, because Google wants you to deploy to a test environment which has the same parameter on the same machines as closely as possible to production, and it wants you to evaluate, right? And then if you're happy with the result, you can create a new AI platform model version, which is actually by sending into the model registry. So this set of slides are a little bit old, and they have made new names for packages of tools that do the same thing, right? So why first look at this question, I'm like, oh no, like I would definitely make a new version and then test the model, right? I would deploy to test environments. I would make a new version and I would test and evaluate the model because I'm a researcher, right? I want to know how different models perform. And even if they don't perform well, I still want them to have a number because I want to be like, okay, that version performed extremely terribly on these specific types. Why, right? I want to be able to do those kind of things. But I guess they're saying you should only make a AI platform model version if you plan to deploy it, and you can still do exactly what I just described if you use the Vertex AI pipeline, because the metadata and the versioning and the model registry is automatically logged for you, right? So that's, I guess, one of the benefits of using a managed platform. Otherwise, it costs you money, but whatever. So a couple quick facts about the test. You can take it online or in person. It's about 2 hours, and for those in the crowd who may be neurodivergent or require accommodations for testing, it is something you can request. I don't know what the process is, but I figured that I mentioned that, make it more inclusive, level the playing field. And then you need to register by going to this link, and you can take it, really anytime you want, right? So don't wait too long, otherwise you're gonna forget. But also you don't need to do it immediately. Based on what I heard, the passing rate is around 70 to 80. They don't give you an exact number. Also, they change the questions on the test all the time. As in, they have a few different questions that test the same concepts, right? Should you use a TPU? Should you use a GPU? But they just use different cases for that, right? So yeah, this is just generic text taking strategies. But once again, what I fundamentally recommend, and this is the plan that I made for myself, is to understand the way Google thinks about machine learning. Like, what are the steps? What is the framework for their AI ethics, for their how to frame a problem, for the different parts of a ML lifecycle, right? And then for each of those box, what are the products that I could use for the set of Google tools, and then I need to understand the trade-offs between those, right? It's the same thing for machine learning. If you have this, machine learning setup with this kind of data, what are the model architectures you should think about? for evaluation metrics and what is the trade-off between each of those, right? So if you're able to understand that in a decent level of detail, you have a good chance of passing. Definitely brush up on first year and second year like stats and probability and distributions and things like that. You should be pretty good. And for the Google product knowledge, especially because the labs are changing and they maybe have not updated all their documentations, I highly recommend taking a foundational model, making it work in a notebook, and then going through every single step of the pipeline using TFX and Vertex AI to do an end-to-end deployment, right? Two reasons. One, if you're looking for a job in the industry and don't have prior experience, those are really good portfolio projects. Make sure you actually use a different data set or actually modify the model a little bit, right? Otherwise, there's no value in your in your interview. You're trying to evaluate your skills. Like if it looks the same, then they're not going to spend any more time. Also, if you're going to use that as a portfolio project, make sure you have proper documentation and write a nice README. And the other reason is if you can somewhat loosely remember the framework and you actually go through the process of applying it end to end for a project, then you have a better chance of being able to make those trade-off decisions easier, right? So with that said, that's all I have to say about this. Yeah, I mean, Roya, I don't know if Roya has time to chime in, but yeah, either in the chat or in the Q&A or whatnot. Okay.
I think there is a question in the Q&A section. I don't know if you answered it.
Yep, I think I did answer that one.
Okay,
Yeah.
I will mark it as answered. Give me just a second. Thank you.
Cool. Good one. Thank you, William. So any other questions? I'll stay on or so. And feel free to ask questions to Roya in the chat. Other than that, I think we can stop recording. Yeah, it's been really honor, guiding you all through this and going through